Hello, Paul here. Today we're going to deal with frameworks and forces in frameworks, which is statics, and this is the framework we're going to deal with. We've got a top member, a member acting down here, a cross member and a member acting up here. So there's basically four members, and we're using Bose notation to denote which member is which. So for example, this top member is member AD, space notation there. And what we're going to do, we're going to find the reaction Ry here, and the nature of the reaction Ry, and the reaction Rx here, and then we're going to find the force in each member, and the nature of that force in each member. Now to do that, to start off with that, I've made a model to try and explain some of these terms, such as the reaction of a force, and compressive stress and tensile stress and what they are. So we'll go to the model first, and then we'll go through each one of these terms and work out the force in kilonewtons of the reaction or the member and the nature of that force. This is my model made to scale, and I've made it out of drinking straws. The framework we looked at is assumed to be pinned to a vertical member like this by two pin joints here and here, and they are assumed to be frictionless pin joints, so they play no part in the forces that we're going to be calculating. We have a 4 kilonewton force acting vertically downwards here, and that 4 kilonewtons force is going to apply a tensile stress, or a tie. It's going to make this member a tie. Because it's acting downwards, it's going to be compressing this member here, and it's going to be compressing this member here, both these members. And both these members then will therefore suffer compressive stress, and they will be known as struts. This member here will have tensile stress because of the force, the component of the force pulling down this way. Now, what do we mean by reactions? A force, any force acting down here, will produce a larger force in this member here. That's because when we're dealing with forces and counterbalancing forces, if I've got 4 kilonewtons acting down here, I need, in order to keep this framework stationary, I need to counterbalance that 4 kilonewtons by a force acting upwards at this point, directly upwards. Because this member is at an angle to the 4 kilonewton force acting downwards, its vertical component, which must equal 4 kilonewtons, indicates that the force in this member must be larger than 4 kilonewtons. If I was to remove this pin joint here, we'll be able to see what will happen with our framework. So we have a 4 kilonewton force acting downwards, and it's going to push this way. It's going to cause a clockwise moment. So reaction X, the reaction at this point of our vertical framework, must be directly opposite and equal to the force acting in by that 4 kilonewton load here. Okay? So reaction X is going to be equal and opposite to the force acting in here. The 4 kilonewton force acts vertically downwards, and in concurrent forces, in a balanced system of 3 forces, if it's balanced, all 3 forces must pass through the same point. So we have a reaction which is horizontal, we have another force, the 4 kilonewton force, which is vertical, and the reaction Ry therefore must pass through this point here, imaginary point down here. The first thing we need to find is the angle of reaction Ry, which is going to pass down there, and that's what we're going to look at initially. So back with our drawing, we can immediately mark some things into the table here. From the framework, we worked out that the nature of the force in member AD would be tensile. So a tensile force is known as a tie. Member DB has or suffers compressive stress. so it's a strut. CB, that's this member here, the cross member, is also a strut because it suffers compressive stress. And CD is a tie because it's going to be pulled downwards by the component of this force down there. That's a tie. Right. To work out the angle of the reaction, Ry here, we can use trigonometry. From our framework, you would have seen that the vertical stanchion, the distance between Ry and Rx was 1.732, and our top horizontal member, we had a distance of 2.732 as well. So when we use trigonometry, we can use the opposite over the adjacent is equal to the tangent of the angle here, and that's what I've got here. So the opposite, 1.732, divided by the adjacent, 2.732, gives us the tangent, and when we inverse that, we get an angle of 32.5 degrees. And that 32.5 degrees is applied here. So reaction Ry acts at an angle of 32.5 degrees to the horizontal member there. To find the reaction Rx, remember we said that we're going to have a compressive stress acting against the vertical stanchion. Rx will need to provide a horizontal force that is equal and opposite to the force acting in here. We take moments about Ry there. Now, Ry, top horizontal member, has a length of 2.732 and it has a force of 4 kilonewtons acting vertically downwards at this point. So it creates a clockwise turning moment of a certain force, and we can find that by taking 2.732 and multiplying it by 4 kilonewtons. And to counterbalance that, at this point, Rx must provide a balancing force, which is the distance 1.732 times whatever force Rx is. And both of those taken together must equal 0 for no rotation to take place. So when we rearrange this equation here, we simply take the minus 1.732 times Rx over to the other side, and then we can leave Rx on the other side and divide this side by 1.732, and we're left with this, and the force, the counterbalancing force, the reaction at Rx is 6.3 kilonewtons. So the force in Rx is 6.3. But one other thing to note, we did say that if Rx is going to have a reaction of 6.3, which is equal and opposite to this horizontal force, then the force in member CB must equal Rx. This is CB here, and it must equal Rx. So we know that CB will be 6.3 kilonewtons as well. To work out the vertical component of Ry, we know that at this point here we must have a 4 kilonewton force working downwards. Therefore at this point we must have a counterbalancing component vertically upwards of 4 kilonewtons. There's two ways of working this out. We can either take the hypotenuse and multiply it by the cosine of this angle, which is 57.5, or we can multiply it by the sine of this angle, which is 32.5. And I've chosen to do that. So this force here must equal the times by the cosine of 57.5 minus 4, this force acting downwards, must equal 0. So we can rearrange that again. Ry cos 57.5 is equal to 4. Therefore, the nature, the force of Ry must equal 4 divided by the cosine of 57.5. And when you do that sum in your calculator, you will find Ry is equal to 7.44 kilonewtons. As I said, there's a couple of ways of doing it. I've chosen, you can see I've made a mistake up here, I've chosen actually to take the cosine route because it's easier to see. We know that this acting upwards must be 4 kilonewtons. So we're simply taking the hypotenuse times the cosine, there, Ry being the hypotenuse, times the cosine, minus the 4 kilonewtons acting downwards, must equal 0. That's vertical components must equal 0 for balance. And when we transpose all of that, we end up with Ry is equal to 7.44 kilonewtons. We've just worked out then that the reaction Ry is 7.44 kilonewtons and it's acting at an angle of 32.5 degrees to the horizontal there. We will now work out the force in member DB here. If I ever manage to get this flip chart thing working.
Modern technology.
Effectively, I have this member which is acting at 45 degrees. There. And we have a 4 kilonewton force, as we know by now, acting downwards. Earlier on I mentioned that in order to counterbalance this force, this member must produce a counterbalancing force at this point of 4 kilonewtons. Therefore, the force in this member must be greater than 4 kilonewtons in order to produce a vertical component of 4 kilonewtons. And this force will be known as the hypotenuse. And we know this force, the adjacent to the hypotenuse, must be 4 kilonewtons in order for balance to occur. And as usual with trigonometry, if we're going to use the 4 as the adjacent, we need the cosine of 45 degrees. It's the same sum effectively as what we did before. So we take the cosine of 45 degrees and we divide that into 4, the adjacent here. And that will equal the hypotenuse, or the force in member BC. I believe it's BC, isn't it? No, it's DB. That will equal the force in member DB. Okay. So when we do that, the adjacent, or the force in dB, divided by 0.7071, which is the cosine of 45 degrees, will give us a force of, wait for it, drum roll, 5.66 in member dB. We'll have a force of 5.66 kilonewtons acting down at 45 degrees. And we can plot that back into our... Could you imagine doing this on one whiteboard? You'd need a whiteboard the size of that wall to do all this, wouldn't you? dB, 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 5.66. Now we'll do member AD, and we're going to stay on this part of the drawing now for AD because I've done enough, I've gone through enough of the process and procedure you need to do. It's effectively the same type of thing over and over. We'll note that if we have a vertical component here of 4 kilonewtons counterbalancing this force here, then it makes sense, does it not, that the horizontal component must equal 4 kilonewtons. This 4 kilonewtons is pulling directly against this horizontal component here. If you were to apply your trig you know that this angle here is at the reaction RY is 32.5 degrees. When you apply your trigonometry to that, you will find that this horizontal component is equal to 4 kilonewtons. I'll let you do that because I'm bored of it. Finally, we have probably the most difficult one, which is CD. Now, what happens with CD is we have a force in this member and it acts down this way here. It produces a downward acting vertical component, which you will find if you do your maths exactly the same as you did here, is 4 kilonewtons there, this downward acting vertical component there. Now, of course, in order to counterbalance this 4 kilonewton force, this tie here must produce a vertical component in the opposite direction of 4 kilonewtons. Therefore, the force in this tie must be greater than 4 kilonewtons. If it's not, then you've made a mistake somewhere. It's exactly the same procedure, isn't it? We know that this is the unknown, this is the hypotenuse, this is the unknown. It produces a counterbalancing force of 4 kilonewtons. And if we think of the 4 kilonewtons as being the adjacent, once again we simply go back to our trigonometry. The adjacent divided by the cosine, and we know this. We should know this angle. If this is 60 degrees, this angle must be
30.
Oh yes. I astound myself by my genius sometimes. And that's going to equal the force in member CD there. When you do that sum, which you can do on your own, I don't need me to do it for you, you'll see that it comes to 4.66 kilonewtons. In conclusion, this is an extremely long-winded, tricky in places thing to get your head around. That's why I made the model, to help people to understand it and to help me to understand it as well. It's certainly if you're going to try and teach it. In reality, in engineering terms, if you were ever faced with doing a lot of these type of calculations, you would be well advised to make a computer model to do them for you, because it's, as I said, extremely tedious, and you've only got to make one mistake and it all falls in a pile of... That'll do.